Hi everyone. So in this video, I'm going to be talking about measurements. That's the overall topic here. We're still in Unit 1, Essential Chemistry Skills. So with measurement comes these 3 points I'm going to go over in the video: SI units, metric prefixes, and how to take precise and proper measurements. So what I want you to do is take your notes out and take notes along with me in this video. So let's get started. First with SI units. So SI, it's basically stands for System International, but that's the French term, so you could call it International System. I'm not going to even try to pronounce it in French, but basically SI is a French term for International System, and it's kind of an agreed upon set of units used by scientists worldwide. Now, I know here in the US, we have a lot of our own kind of unique units that we still kind of cling on to, even though most of the world has moved on. However, science is still done in the universal language of science, which is the SI system. So even though you might drive your car in miles per hour, if you're taking measurements in a physics lab and reporting that data, it's going to be in meters per second or something like that. So when it comes to systems of measurement, we pretty much have two competing systems. We have the SI system, which, as I just explained, is the international system of units. We use the term metric system pretty much interchangeably with this. You can think of SI as the metric system. And then we have the USCS system, which is United States Customary System. These are basically these classic American units, which really were British units carried over here. Although from the most part, from what I understand, Britain has kept some of these and discarded some others. In fact, there are some units they use over there that we think are very goofy, like they'll often measure people's weight in stone, things like that. Anyway, let's just list some of our base units here. I want to start with the USCS, just so you understand what I mean when I say these American-style units. So if you want to find a volume here in the United States, what are you going to measure that volume in? Well, you're going to go with your gallons. You're going to go with cup, pint, quart, teaspoon. I don't need to write all these. You get the idea. If you want to measure something's mass, well, we normally think of mass in everyday language as weight, which would be measured in pounds. There is actually a USCS unit for mass. It's blanking me right now. Probably should have looked that up before I started the video, but it's used so rarely, it doesn't even warrant being listed here. Of course, we're going to talk about the SI unit for mass because that's used all the time in the metric system. For length, if you want to measure lengths here in the US, what are we going to measure in? Well, we're going to measure it in feet, we're going to measure it in miles, we're going to measure it in inches and yards, and we have all sorts of units like this. So these are just some examples of USCS units, and we're not going to be using these to measure things in the science lab. Science worldwide is done with the SI system, so we're going to use our SI units. Now let's go through what those SI base units are. I say base unit because you can take any base unit and apply prefixes to it. For example, you probably know this, the base unit of length. It's the meter, but you've also heard of centimeters, millimeters, kilometers. Those milli, centi, killi are prefixes that you put on the front of it to change it. So the SI base units, the base unit for length is the meter. And I want you to write down not just the word, but the abbreviation, the symbol for it. And this is going to be a lowercase m, not a capital M. The SI base unit for volume, think about it. I'll bet you know this. It's the liter, which is a capital L. But there's yet another way of representing volume using SI units, and I don't mean like milliliter. Think of volume. If you were to measure the volume of something, you can either, pour the amount of water in it, or pour its contents in a graduated cylinder and get the liters that way. But what if it's like a square shape? You could measure the length, width, and height, multiply them together to get volume. So what's your base unit going to be if you measure length, width, and height? Well, if the length and the width and the height are all in meters, it's going to be meters cubed. So let's say for volume, it's going to be the liter or the meter cubed. If it's area, that would be squared. Length times width would be meter squared. Now keep in mind, when we say meters cubed, that can also mean centimeters cubed, kilometers cubed, and so on. The SI base unit of mass. You're probably thinking gram, but technically it's not gram. It's actually the kilogram. And I know that almost doesn't fit the rest of them because why would it be kilogram with the prefix in front? It's just the way it is. And I'm sure actually the physics teachers could probably better explain this. I know a lot of the more advanced units, like something I believe I mentioned in class already, a unit of energy is called a joule. Technically, a joule is a kilogram meter squared per second squared. I am about 80% confident on that. If you break down the base unit, the kilogram acts as the base unit of mass. So kilogram. And a kilogram is abbreviated lowercase k, lowercase g, like that. Let's go over some other SI base units. I'm going to clear some space here. Let's go over some more SI base units. So the SI base unit for, let's go something like the SI base unit for energy. I just kind of mentioned this. It's going to be the joule, J-O-U-L-E, abbreviated a capital J. We're going to talk about joules later. Another common unit you may have, I'm sure you've heard of this, you may not think of it as energy, it's calorie. A calorie is a unit of energy. I mean, why do we say food has calories? Well, if you eat like a Snickers bar and it has 320 calories, that means that your body is obtaining that much energy from that Snickers bar. There's two more SI base units I want to talk about. One of them is going to be temperature. And there are two units that you're going to see in a chemistry class. The most common one is going to be degrees Celsius. We generally will not use Fahrenheit in the science lab. And the other one's going to be Kelvin, degrees Celsius or Kelvin. And Kelvin is a capital K Kelvin. Notice I didn't say degrees Kelvin. It's really supposed to just be Kelvin. We're going to talk a lot later about what Kelvin means, but think of Kelvin as like a true or an absolute temperature scale. For example, they're saying it's going to warm up later this week. So let's say overnight, a couple days ago, it was like 35 degrees Fahrenheit. And in the middle of the day, later this week, it's going to reach 70. So go from 35 to 70. Well, 35 to 70, that's twice as much, right? Can you say it got twice as hot? Well, no, because, the Fahrenheit scale is just a number scale. And, if we converted that to Celsius, it wouldn't be twice as much anymore. And even if the Celsius were to double, let's say it's, 16 degrees Celsius one day and 32 degrees Celsius the next day, which 32 Celsius is going to be quite hot. Is that double? No, because those are relative temperature scales. However, the Kelvin temperature scale is a true temperature scale where 0 Kelvin is no temperature, no heat, no particle movement. It has a special name, absolute zero. And in fact, it can never be reached. According to the laws of chemistry and physics that we know, absolute zero cannot theoretically be reached. Now, I'm sure if you Google this, you will find some weird workaround explanations where technically we reached absolute zero. I've heard we've gone beyond absolute zero, but never actually been absolute zero. It's one of these things that will often create an argument. But theoretically, Kelvin should never be zero because that's when all the particles would stop moving. And of course, we know the law of conservation of mass and energy. Energy can never fully be lost like that. Long way to explain what a Kelvin is. But in short, a Kelvin is a unit of temperature that we're going to talk about a lot later. It's very useful for math equations, which we're going to get to in Unit 2. There's one more SI base unit I want to get to, and that is, it's not going to make much sense now, but I want to mention it. The amount of a substance. Now, when I say amount, I don't mean its mass, and I don't mean its volume. Normally if I say the amount of substance, I got like a gallon of gasoline, or I've got like 16 pounds of iron. When I say amount, it's really like counting the actual number of things. The base unit of this is something called the mole. M-O-L-E, which we abbreviate as MOL. You're going to save tons of time this year abbreviating that. M was already taken by things like meter. So the amount of substance is a mole. You know how the word dozen means 12 of something? The word pair means 2 of something? Well, the word mole just means 6.022 times 10 to the 23rd, which you don't need to write this down. Oh, I didn't mean to delete that. Hold on, let me get that back. Please come back. Where's my undo button? Yeah. 6.022 times 10 to the 23rd. It's a very large number. It's 602 followed by 21 zeros. 2. Okay. You don't need to write this down. We're going to cover this when we get to unit 4 or 5 this year. It's a large number of something. Now, what could we possibly be measuring, or I should say counting, that would warrant one of them to be this many of them? And the answer is obviously atoms or molecules. So when it comes to counting particles, we'll eventually be using the mole. Okay. These are the SI base units, but we now need to talk about SI prefixes, because you're not going to get by just using meters or just using liters. You need to be able to put milli, kilo, centi, and all the other base units on there. Now, when it comes to these, or I didn't say base unit, I meant to say all the other prefixes. So these are going to be our metric prefixes. Pre meaning before, so prefixes come before the base unit. So what I want to do here is mark the base unit. And it's important to me to put this here, because if you just go with what's below and above and skip the base unit itself, when you're counting how many times bigger, it's easy to get that mixed up. Let's start with the larger SI prefixes, the metric prefixes. Well, you may have heard of kilo. I'm sure you've all heard of kilo, kilogram, kilometer. You may have heard of some of the even larger ones, like mega. A less common one, and from what I understand, you guys did a little of this in middle school, going over your, King Henry died drinking chocolate milk type phrase. If we go one step above the base unit, it's a very rarely used unit called deca, which I've seen spelled 2 ways. I've seen it as DECA and DEKA. Either way is fine. This is honestly used so rarely I often forget. But the abbreviation for deca is DA. If we go above deca, we have another rarely used unit called hecto, which is H. And if we go above that, here's our good friend kilo, which is K, lowercase k. So we have a lowercase k, lowercase h, and lowercase da. And really, I should put a line here, because like a dash or hyphen, because these are prefixes which come before. Now, how many times bigger are these? Well, the idea behind the metric system is it's in units of 10. So this is 10 times bigger. 1 decameter is 10 times bigger than a base unit meter, or liter, or gram. Hecto is another 10 times. So how many times bigger is hecto compared to the base unit? It's not 20, it's 10 times another 10, it's 100. Hecto to kilo, there's another 10 times. So how many times bigger is a kilometer or a kilogram compared to a base unit gram? No, it's not 30, it's 10 times 10 times 10, which is 1,000. I plan on doing one slide with kind of the common rapid fire conversions you should be able to do in your head. For example, if I say a kilogram, you should be able to tell me that's 1,000 grams rapid fire. We'll come up with some of those. All right. You know what? I'm running out of room here. What I'm going to do is shift this down a little bit. Sorry if you didn't leave yourself enough space. I should have clarified that we'd be going up, even though we normally go down with notes. So above kilo, there are some other base units that are rarely used in a first-year chemistry class. Certain industries will use it all the time. And the next one we're going to talk about is mega. And mega has a capital M, not to be confused with a lowercase m, which is either going to be milli or is going to be meter. And in fact, when we get to millimeter, it's going to be lowercase m, lowercase m. Mega. Now, mega is not 10 times bigger than kilo. It's 1,000 times bigger. So we start really jumping up. So how many times bigger is mega compared to the base unit? 10 times 10 times 10 is 1,000. And then it's another 1,000. What's 1,000 times 1,000? 1 million. So mega means 1 million. And if anyone here is computer savvy, you might know that a megabit or byte, you probably know which term is the right one. And I think they're different things, but there are 1,000 megabytes in, sorry, I said it wrong. There are a million bytes in a megabyte. What's beyond mega? Computer savvy people would know giga. Giga is a capital G, and this is yet another 1,000 times bigger. What's a million times another 1,000? Add 3 zeros, it's a billion. So there are 1 billion base units in a giga. Now, to put that in some perspective, we think computers a lot. There are 1 billion bits or bytes in a gigabit or gigabyte. Comparing giga to mega, it's 1,000. So if you have 1,000 megs, 1,000 megabytes, you have a gigabyte. I think in terms of computer memory, because when I was growing up, we of course had floppy disks, which I think were 8 megabytes of storage. No, it was even maybe like 256 kilobytes of storage. And then we got CDs, and then the first what's it called? Thumb drives came, and I think I remember they were like, God, how many were they? You know, a number of megabytes, definitely not a gigabyte. But now you can buy for like $6. You can get like a 50 gig thumb drive. And really, you can even go higher than that. A lot of times an external hard drive will be 1,000 gigs, which computer people know is a tera. Do it in the same color. Tera, which is a capital T, a terabyte. A terabyte is a trillion bytes, or 1,000 gigabytes. All right. Now, this keeps going for quite a while. In fact, I can't even go from memory above this. I know there's something like a yada and exa. I think exa might be the next one. But anyway, we use these so rarely, it's not necessary for me to know these off the top of my head. Now, what do you need to know for this? That's probably what you're wondering. This is a lot to memorize, right? Here's what you need to know. The base unit, obviously, meter, liter, gram are the 3 common ones. And you have to know kilo. Deca and hecto are useful to know so you can like count orders of magnitude. When I say orders of magnitude, I mean something being 10 times bigger than the thing before it. If you're trying to solve a problem and you're off by an order of magnitude, that's not a good thing. That's because the answer was 6,000 and you got 60,000. Or the answer was 6,000 and you got 600. That means you're off by 10 times. That's 1 order of magnitude. So it's useful to know what these are. But here in the chem lab, in a first-year chemistry class, be familiar with kilo, be familiar with the base unit. Now, we are going to go smaller, and there's obviously more units down here. Okay, so let me think how I want to do this. Yeah, I'm out of space here. So I'm going to not delete that. I'm just going to do a new slide. Hold on, let me clear that. Undo, maybe. There we go. All right, let's go with the smaller Greek prefixes now. So starting still at our base unit here, if we're going 10 times smaller than this, we get to a unit called deci. Not a unit, I misspoke there, a prefix, deci. So a decigram is 10 times smaller than a gram, or in other words, there are 10 decigrams in 1 gram. Decimeter. If a meter is about 3 feet or so, approximately, a meter is about a yard. It's like 90% similar. There are 10 decimeters in a meter. So a decimeter is like, well, it's 10 centimeters. It's going to be about that much. All right, deci. So here the difference is, I'll go red with this. It's 10 times, but it's 10 times the other way. This is 10, the deci is 10 times smaller than the base unit. Smaller than that, good old familiar centi. Centi is another 10 times smaller. So how many centimeters are there in a meter? 100. How many cents are there in a dollar? 100. How many centimeters are in a meter? 100. The next one down, milli. Oh, I forget my abbreviations. Sorry. Deci is a single lowercase d, not to be confused with DA, which is deca. Centi is a lowercase c, and milli is a lowercase m. This is another 10 times. So 10 times 10 times 10 is 1,000. So how many millimeters are in a meter? The answer is going to be 1,000. All right, if I look beyond milli, the next unit down is going to be 1,000 times smaller than milli. Not 10 times smaller, 1,000 times. And it's micro. Micro. Now the symbol for micro is the Greek letter mu, mu. It looks kind of like, sort of like a U, lowercase u with an exaggerated like tail in the front, kind of like this. That's a pretty good mu right there. Often when you see it printed, it'll look like this with a straight down line, like this. Oh, hi, Dr. Smith. Let me pause this real quick.
You recording? What are you doing?
I am recording. Okay, I've actually never paused a recording before. Hopefully this is nice and smooth. Let's continue. Someone came in, so I put the mask on. I talk. Micro. So when you see it printed, it often will look like this. Like if you were to Google micrometer right now, you'll probably see that. So these are kind of the two abbreviations you'll see. In everyday language, this is sometimes called a micron. There's actually a tool called a micrometer, which measures distances in microns. Now, I know the term micrometer is spelled exactly like the term micrometer, but technically they're different things. A micrometer is a unit of distance. A micrometer is a tool that measures tiny distances. If you want to envision what a micrometer is, put your two fingers together as close as you can without them touching. That's going to be about a millimeter. A micrometer is 1,000 times smaller than that. So imagine that little space between your fingers, cut that down 1,000 times, that's a micrometer. You're not going to be able to see anything that's a micrometer in size. Very small. Now, let's go smaller than micrometer. The next one down is nano, a nanometer. The abbreviation for this is a lowercase n. And if you're into the cutting edge research, AI technology, advanced medical research, you may have heard of nanotechnology. The idea being if we can manufacture some kind of man-made synthetic germ-killing robot, that would be nanotechnology, where we're dealing with things on the nano scale. A nano is going to be, oops, I forgot to finish this, 1,000 times smaller than this, and 1,000 times smaller than this. So if we compare, remember, from base unit down to milli is 1,000 times smaller. Micro is another 1,000. Nano is another 1,000. So we're talking now about 1,000 times 1,000 times 1,000, which is a billion. Billion times smaller. We'll do one more. Down here we have pico. Skiers might call this pico, but in chemistry terms we call this pico, lowercase p. Yet another 1,000 times smaller, meaning we are now a trillionth of a meter, or in terms of grams, a trillionth of a gram. All right, so we have our base units here, deci down to pico. Now there's, I said it, pico. I just want to do one more slide. If you, in your notes, are able to have both of these like merged, where it's just like from tera straight down to pico, you would be able to see all of these. Oh, sorry, something I forgot to mention here, which is worth noting. Which ones do you actually have to know? And when I say no, I mean like memorize for future testing quizzes. Only the common ones, meaning the base unit, which I marked before, centi, and milli. I mean, it's good to be familiar with these terms. So if you see micro, nano, and pico, you can be like, hey, I recognize that term. But in terms of what you have to like be able to work with, just centi, milli, base unit, and kilo. Just those four. The four common ones that I'm sure you already knew coming in. I just want to do one quick slide showing kilo down through milli. So kilo, hecto, deca. Don't forget the base unit. You got to include the base unit or this order gets messed up. Base unit. Kilo, hecto, deca, base unit, deci, centi, milli. Okay. Um, if you want to quickly convert, you can using like sweeping zeros or just like doing the math in your head, converting between these. However, I'm not gonna say I discourage it, but eventually we're gonna work with conversion factors, which is a more advanced, I say advanced, and it almost acts like it's not gonna be a good thing. It's a more efficient way, in my opinion, of converting between units. But if you did want to convert, let's say, kilo down to the base unit, you count how many steps we take. 1, 2, 3 steps. And it's 3 steps smaller to get to base unit. Or in other words, there's the base unit being smaller, we'll end up with a large number of them. So for example, if we have 3 kilometers, how many base unit meters is that going to be? Well, picture what 3 kilometers looks like in your head. It's going to be about a little under 2, well, probably about 2 miles. How many meters are going to be in 2 miles? Very few of them or quite a lot of them? Obviously, it's going to be quite a lot. So in this case, we moved it 3 times. So we take our 3, we grab the imaginary decimal point, and we sweep it 3 times to the right, fill in our zeros, and we get 3,000 kilometers. Okay? Let's say we have centimeters. Let's say you have 14 centimeters, and I want to determine how many decameters, deca, D-E-K-A, or D-C-A, which I often will spell it D-E-K-A. Either spelling is acceptable. Well, let's count how many steps. So from centi, we go 1, 2 to the base unit, and 3 here. So in this case, since my unit is getting larger, my number has to get smaller to balance that out. So I'm going to grab my imaginary decimal point after the 14. I'm going to go 3 times to the left. 1, 2, 3. Fill in the 0. It's going to be 0.014 DAM. Now, I'm not cursing at you. Decameters, D-A-M. Okay? Front 0 is obviously optional. I tend to always use the front 0. You don't have to. You could just say 0.014 DAM. You probably have some kind of saying for this. When I was in school, they taught us King Henry died, mother didn't care much. Now the mother is our base unit meter for M. In fact, one of the more edgy teachers went with King Henry died, damn, because of DAM, decameter. King Henry died, damn, mother didn't care much. Remember, this only works if you include the base unit. I know I've heard Wilton students tell me different little phrases, so depending on your teacher, you've had some kind of phrase there. So these are our prefixes. I want to sum up the rapid fire conversions that you should be responsible for. I'll call these rapid fire conversions. Now, at this point in the year, we're going to start to see the difference between Chem 2 and Chem 1 emerge. And as I mentioned at the start of the year, it's really just for assessments, for tests and quizzes. But these rapid fire conversions, Chem 1s, you'll likely see these on your assessment written. Chem 2s, you got to know. So we should know kilo. So for example, 1 kilometer equals 1,000 meters. Now remember, the base unit can be swapped out. You could put kilograms equals 1,000 grams. The base unit can easily swap out. We should know, for smaller units, you should know what centi is. So 1 meter equals 100 centimeters. And again, we can convert that, change that to liters or grams. We should know milli. 1 meter equals 1,000 millimeters. And because of these bottom two, you should be able to like combine them. Well, what's the relationship between centi and milli? Well, a centimeter is 10 times bigger than a millimeter. So you should be able to tell me that 1 centimeter equals 10 millimeters. Okay. So these are kind of the 4 rapid fire conversions that you should be expected to work out in problems, because these will come up. I mean, eventually we're going to work with, 3.02 kilograms of sodium bicarbonate. Well, you would just have to quickly say, all right, so it's kilograms. So it's, 1 kilogram equals 1,000 grams. So I'm going to divide it by 1,000 or multiply it by 1,000. You're going to end up multiplying it by 1,000 like that. Okay, so I probably have about 5 or so more minutes, maybe a little longer. I'm going to talk about taking precise measurements, because now that we have our metric SI units and our prefixes, we need to now be able to apply these to take some actual measurements. Okay, here's what I mean. All right, imagine that is a ruler, and you're trying to measure, well, let me go like this. 0, 5, okay, and sorry, this is not going to be to scale. 1, 2, 3, 4, okay, good enough. So let's say you start with an object at 0, and the object is that long. What would you call that? If I were to take that measurement, what would you say? Well, 1, 2, 3, 4, 5. It's between 3 and 4, so I'd call that 3.4. You know how to do this. This is common sense. What you don't realize what you're doing, the proper technique here, well, actually, I should say, we should find out what unit this is. Let's say this is centimeters, so that would be 3.4 centimeters. What you're doing here, just by taking a guess at something like a 3.4, is you're saying, I know for a fact that this number is between this line and this line. That's 3, that's 4, so I know it's a 3. And I am estimating one digit. You always estimate one digit. I estimated that to be a 0.4. I'm curious if anyone estimated it to be a 0.3. If you did, you're just as right as I am. I'm just as right as you are. That last digit is your estimate. Now look, if you're way off, then yeah, it's not going to be right. Like if you say 3.7 for this, come on, that's nowhere near 3.7. But if you say 3.3, 3.4, you know, even 3.2, 3.5, you can even argue, that's acceptable because that last digit is your best guess. Similarly, what if we have that right there? So that's between 1 and 2, and I'd go with like a 1.3 for this, and that would be centimeters. 1.3, 1.2, you know, again, this is common sense. You already know how to do this. Now, what if I change this up? What if, new scale, we'll call this 60, 0. All right, so 10, 20, 30, 40, 50, 60. So let's say that's 30, 40, 50. Okay. I want you to think about what you would call that. What do we know? We know that this falls between 20 and 30. So we know the first number is going to be a 2. Now we guess, not guess, but we do our best estimate. And our best estimate for this is that it's going to be like a 7 or an 8. That's your judgment call. I'm going to go with a 7 here. And again, if this is, let's say, meters, then this would be 27 meters. Am I going to guess beyond that? No. You're not allowed to. If you're taking a proper measurement, you're not allowed to go beyond that. You're not allowed to say, you know what? I keep flipping between 27 and 28. I'm going to split the difference and say 27.5. You can't do that. The quality of your measurement depends on the quality of the tool you're using. Notice how this measuring tool had one line for every single centimeter. 1 centimeter, 2 centimeters, 3, 4, 5 centimeters. This tool had a line for every 10 centimeters. 10, 20, 30, 40, 50, 60. So for that reason, we get a less quality measurement out of this one. What do I mean by less quality? This one measures to the ones place. This one measures to the tenths place. If you want to think about it in another way, look at the ruler you're using. The ruler you're using, whatever the digits are, your final answer is going to be one step beyond that. This ruler goes to the nearest whole number. You're going to go one step beyond that and measure to the 10th place. This ruler has lines for every 10 centimeters. You're going to go one step beyond that and measure to the ones place. Let's do another ruler. All right, let's say this is 3 and 0 centimeters, 2, 1, and then we have this. Notice a difference. This ruler is of higher quality than the others because it measures to a further degree. This has lines for every 1, 2, 3, 4, and it has lines for every 1/10 of a centimeter. Technically, these are millimeter lines because every 1/10 of a centimeter. So let's say the measurement falls right there. Judgment call depending on which pixel you're using. What are you going to call it? Well, 2 to 3, 2.1, 2, 3, 4, 5, 6. That's 2.6, that's 2.7. I'm going to call that about 2.65 centimeters. Why do I say that? Well, I know that it's between 2 and 3. Here's my 2. I know that it's between 1, 2, 3, 4, 5, 2.6 and 2.7. And I'm going to guess that it's exactly halfway through. So there's my 6.5. Please do not overthink this. If I just started this with this slide, I guarantee you all would have said something like 2.65. Please don't overthink it and be like, all right, Mr. S says we need to think about everything we know and then take one extra guess. Don't overthink it like that. Your final answer will reflect this level of thinking. Just to show you that it matches what I said before about going one extra degree beyond your ruler. This ruler measures to the what place? It measures to the 10th place, which means your measurement is going to be one step beyond that to the 100th place, which this is. Last thing I'm going to cover in this video, what if it falls on a line? What if it falls on a line? Let's go all the way back here. What if my new measurement is this one? Now I'm going to do my best to make it hit the line. It might not, but just pretend it does. All right, pretend that's right on the line. And you want to measure this. What do? Are we going to call that 2? Are we going to call that 2.0? Are we going to call that 2.00? What are we going to call it? The best way to do this is to say to yourself, what if it didn't fall on the line? What would I call it? You know, let me use my disappearing ink for this one. What if it fell right there? What would you call that? Well, that's 2 and that's 3. That's probably about a 2.5, maybe a 2.4. So if I'm going to call that a 2.4, you're going to match that same level of detail of the decimal places. So if that's a 2.4, then you're going to call this 2.0. That's the one you want. So the best way to do it is to just go off the line. Imagine it's off the line, and you're going to match that same level. And this makes sense because your estimate, what you know is that it's on the 2. Your estimate is that it's exactly on the 2. I know I phrased that a little strange, but you know that it's pointing at the 2, not the 1 or the 3. And your decimal point estimation is that it's exactly on there. You might be a little off, and you might say 2.1 or 1.9. Either of those would be acceptable as well. Another way to look at it is to just look at the ruler and ask yourself, what will our measurement be if it's always 1 better? This measures to the nearest whole number, the ones place. So your estimate's going to go to the 10th place, 2.0. What if you want to measure that one? Well, that's right on the 50. Are we going to call it 50? Are we going to call it 50.0? 50.00? Well, this one's actually a little trickier than it looks. You're going to call it neither of these. And this is something I'll probably have to clear up at a later time because I know I'm like down to my final minutes here. You're actually going to call this 50 point. Let me just briefly explain why. We're going to learn something called significant figures at a later date, probably later this week. The number 50 has one significant figure. That 0 is important, but it's not considered a sig fig. A sig fig adds to the precision, the quality of that number, and this 50 doesn't. That 0 doesn't. In fact, it rounds it off. This 50.0 is 3 significant figures. Why do these zeros count, but this 0 doesn't? Because these zeros, the purpose of those zeros is to add to the quality of that measurement, not take away from it like this, to add to it so they count. In this case, if we want the number to represent the ones place being the last known, like our estimate, the last digit, you can't leave it at 50 because 50 by itself is technically rounded to the nearest tens place. But if we want 50 rounded to the nearest ones place, the sort of cheat that we use is you put a decimal point after the 0, and that shows that it's rounded to the nearest ones place. Complicated example, we will cover this in more detail later. Let's just do the last one here before we go. All right, I'm going to do 2 arrows. Here. Wait, I wanted to aim on the line. Okay. Just pretend that one's on that line. And here. Okay. So this one, I tried to point to the line that's at 1.2. So are we going to call that 1.2, 1.20, 1.200? What are we going to call it? Well, you say, well, what if it fell off the line? We already did that. One of the lines was 2.65. So you're going to match that same level of detail. So if this is 2.65, you're going to go 1.20. What about this one? I'm trying to make it right on the 2. What am I going to call it? Are we going to add an extra 0 like we seem to always do? Not in this case. If that fell off the line, you might call it 2.65. So here, we're going to call it 2.00. It's not about deciding how many zeros to stick onto it. It's about matching the same level. Because notice at this point, this is to the nearest hundredths place. This is to the nearest hundredths place. This is to the nearest hundredths place. Okay? The other way of looking at it would be to ignore all these arrows and just say, hey, look, if this measures to the nearest tenths place, we're going to go one step beyond that and measure to the nearest hundredths place. That's all there is to it. Okay? So we will, of course, review this. None of this is going to be on that quiz, which you have coming up near the end of this week. This is going to be kind of the next concept. Okay? So I hope this all makes sense. Thank you for watching.